While Masha's getting set up, we did not leave a ton of time for questions, so all presenters will go make themselves available during breaks. So just feel free to grab folks if you have questions, and you can have discussions in the hall. Okay, so with that, I am so excited to introduce Masha, one of the co-creators of Vlogs, to give the second keynote of the morning on Axiom. So Masha, I will pass you the mic.
Thank you so much. Welcome, everybody. Give us a few seconds to set up, and we'll begin shortly. Thank you so much for helping us set up. I think we're good to go and get started. I'm Masha, and today I'll be talking about Axiom, a composable C++ framework for building query engines on top of Velox. If you take one thing away from this talk, let it be this. Velox made execution composable. Axiom extends that to the full stack: parsing, analysis, optimization, and runtime. By the end of the talk, I'd like you to ask, can my engine be built on this? So what do we mean by composable? Think of Axiom as Lego for query processing. You have a set of reusable pieces, an API, optimizer, runtime, and you can snap them together in different ways to build different engines. The pieces are compatible, but they don't restrict how you put them together. You can swap components, extend them, or replace entirely. The key insight is that these pieces shouldn't have to be rebuilt for every new engine. Today they are, and teams spend significant time building a foundation that looks much like everyone else's before they get to the unique value their engine was meant to deliver. Axiom lets you skip that and start where it matters. For existing engines, rebuilding on a composable foundation unlocks new deployment modes and APIs. The same engine can run embedded on a laptop or distributed across a cluster with streaming or durable shuffle, and offer both SQL and data frame APIs. That's the vision. And if it sounds familiar, it should. It's the same vision that drove Velox, extended to the full stack. Velox provided a reusable library of efficient operators and allowed teams to rebuild the execution layer of Presto through Prestissima and Spark through Gluten on a shared foundation, delivering 2 to 3x efficiency gains across the board. Data processing for AI training pipelines was also rebuilt on Velox, gaining not just efficiency, but reliability and functionality that had originally been built for Presto and Spark. That's the power of a shared library. Every engine benefits from every other engine's investments. And because the operator library is shared, IBM and NVIDIA can build GPU-native implementations once, and any engine built on Velox can adopt them. That's a remarkable success story. But here's the thing. Velox solved composability for execution layer. But everything above, parsing, optimization, coordination, remains monolithic and engine-specific. Each engine has its own full stack above Velox, and those stacks don't share anything. That's the gap we set out to fill. But before we show you how, let's look at why this matters for users and developers. Real-world data workflows don't fit neatly into one engine. You might start with a streaming pipeline, run batch transformations, prepare training data for AI models, build interactive dashboards, and debug issues along the way with ad hoc queries. Today, each of those steps uses a different engine. Some with SQL, some with Python data frame APIs, all with different semantics, different tools. And the logic across those steps often overlaps. So inconsistencies between engines don't just slow you down, they cause real bugs. Then possible users try to stick to one engine. Presto can handle both interactive and batch workloads, so most teams start there. But inevitably, data volumes grow. Queries that used to work fine start hitting memory limits or running so long that reliability suffers. The workaround of stretching Presto beyond its sweet spot breaks at the worst possible time, and suddenly you're facing a rewrite in Spark SQL. This problem is so real that we built Sapphire, Presto on Spark, specifically to let users run Presto on Spark runtime without modifying the queries. That's inherently awkward. We are bolting one engine onto another. And neither Presto nor Spark gives you a practical local development experience. Want to lint your SQL or test your logic against sample data? You need a cluster round trip every single time. That's the user side. Now, the developer side is not much better. The architectures are split along language boundaries. In Prestissima, Java handles SQL parsing, optimization, orchestrates distributed execution. C++ handles local execution through Velox. They talk over RPC, which is relatively clean, but connectors are split. Metadata lives in Java, data reading in C++. Constant folding is a real pain. It has to happen on coordinator in Java, but produce results consistent with Velox execution. Right now that's solved with a C++ sidecar, which works, but somewhat clunky. Gluten has a similar split. Spark handles parsing, data frame API, optimization, distributed execution, all in Java. Velox handles local execution. They talk over GNI, which is more complex and harder to debug. Both coordinators are monolithic. You can't add data frame API to Presto. Can't run Spark SQL on Presto coordinator or Presto SQL on Spark. You are locked in. So if the problems are clear and the need is real, why hasn't anyone built a unified C++ stack before? We believe the major blocker has been the lack of a reusable C++ query optimizer. Optimizers are extremely hard to build, even with AI. The closest thing to a reusable optimizer in the industry is Catalyst, and it's widely adopted, but it is Java. So when Velox came along, the natural path was to plug it into existing JVM coordinators. Building a C++ optimizer from scratch just wasn't a realistic alternative until now. Axiom is that missing optimizer and more. Let me walk you through the architecture. It comes down to composable components connected by stable contracts. At the top, you have the front ends. Each one, Presto SQL, Spark SQL, PySpark Data Frame API, has its own parser and analyzer. They are independent components, but they all produce the same thing, a dialect-agnostic logical plan. That's the first contract. The logical plan describes what the query does, not how to execute it. It is deliberately compact. A single logical join node says what to join. The optimizer decides how. Hash, merge, index, nested loop. Any front end that produces a valid logical plan can use the same optimizer and the same execution stack. That's what makes it practical to add a Spark SQL parser or a PySpark data frame API without touching the rest of the system. The logical plan feeds into a cost-based optimizer, which produces a physical plan targeting Velox operators. That's the second contract. The physical plan goes to a runtime. Axiom ships with a local runner for embedded single process execution. Axel, which I'll get to shortly, is a distributed runtime built on Axiom. And you could build a streaming runtime on the same foundation. Now, I said the optimizer is the hardest piece. Let me show you why building it in C++ right next to Velox makes the difference. The optimizer directly uses Velox's function registry and expression evaluation, making Velox the single source of truth. No more ensuring that Java's function registry matches exactly, which has been a source of bugs. Constant folding uses the same code path as query execution. No sidecar, no integration overhead. The optimizer can even constant fold scalar subqueries by executing them in process. The optimizer targets Velox operators directly. For example, when planning in or exist subqueries, it uses the semi-filter join operator. Then planning except all counting join. Both are specialized Velox operators that Presto's optimizer is not aware of. It plans a sequence of more generic ones that have to be squashed together in the Presto to Velox translation layer. Building the optimizer in C++ right next to Velox eliminates an entire class of integration problems. Beyond the optimizer, a query engine needs to parallelize work and orchestrate data access. That's where connectors and the runtime come in. Connectors in Axiom are unified. Planning time logic metadata, statistics, partition pruning, and execution time logic, data reading, both parts are in C++, so they interoperate naturally. In Prustissima and Gluten, those are split across Java and C++. The optimizer produces a physical plan, a set of Velox plan fragments connected by shuffle boundaries. The deployment topology is an input to the optimizer, so shuffle costs affect join ordering and other plan decisions. The runtime takes the physical plan and orchestrates execution, embedded in a single process, distributed with streaming or durable shuffle. The user experience stays the same. Same SQL or data frame API, same semantics, regardless of the deployment mode. No query rewrite, no migration. You literally iterate locally using SQL or Python, and then ready, run at scale on a cluster. That's the architecture, and we've talked about this before. This time, we're building it and have early results to share. All TPCH queries work end-to-end, producing optimal plans. We're actively migrating production workloads at Meta. Optimizer and execution stack are handling real queries at scale, not just the benchmarks. Axiom includes an interactive CLI that lets you run SQL locally against TPCH data, local Hive, in-memory data. This has become a popular tool internally. People love sub-second SQL linting and validation without waiting for a cluster round trip. We're also extending PrestoSQL with user-friendly features inspired by DuckDB, from first syntax, trailing commas, method call chaining. We're committed to continuing to modernize the language to make it easier to use. That's Axiom's foundation. Let me show you how it extends to distributed execution. Axel is a distributed query engine built entirely on C++, on Axiom and Velox. Reuses everything I just described, the parser, the optimizer, the connectors, and adds the pieces we need for distributed execution. Admission control at the entry point, a distributed scheduler, and Velox workers. The key point is what the Axel team didn't have to build. The team didn't write a parser, didn't write an optimizer, didn't build connectors. All of that came from Axiom. The team focused on the distributed coordination layer, scheduling, fault tolerance, resource management. That's the composability promise in action. Axel currently uses streaming shuffle, targeting interactive workloads, the same space as Prustissima. We're adding durable shuffle to support batch with fault tolerance that Spark users expect. We're still early in the journey, 1%, 0.1%, whatever your single-digit number of choice. But we've seen a lot of excitement and enthusiasm around Axiom across Meta. As we build it out, we are learning that first, the architecture works beyond our regional use case. The Graph Query team built a Cypher front-end on top of Axiom. They produce Axiom's logical plan and use the optimizer's cost-based join reordering for graph pattern matching. The logical plan and optimizer work for non-SQL languages as well. Both the streaming and AI training data processing teams adopted Axiom's PrestoSQL parser to offer a SQL interface alongside their existing Python data frame APIs. Second, users love local sub-second SQL linting and testing. Being able to validate your query instantly without a cluster round trip changes how people work. Third, composable architecture demands crisp contracts between components. It's harder to build than an analytics system, but that discipline pays off in extensibility, reuse, and ability to evolve components independently. What's next? Still a lot to build. Spark SQL parser, PySpark data frame API, closing the gap between PrestoSpark users, making optimizer truly extensible, adding index merge joins, durable shuffle for batch workload with fault tolerance, and the connector ecosystem is ready to grow. Velox made execution composable and delivered massive efficiency gains. Axiom extends that same vision to the full query processing stacks. The pieces are there. Come help us put them together. Any questions if we have a moment?
Thank you, Masha.
Thank you.
Okay, so we are in break now. We have, I think, about, let's see, our next session is at 10:40. So we have just under half an hour. A few notes. One is we are welcome to use the micro kitchen next door. Just don't everybody go take everything all at once. We should also have maybe some stuff out as well, but we are welcome to that. So we'll be back here at 10:40. All right, thanks.